So finally, it's time to discuss what is PN junction. A PN junction is a device which is made with a P-type semiconductor and N-type semiconductor. Most commonly used material is silicon. So before I jump into the PN junction, let me refresh all the ideas very quickly. I have presented them in a way more detail previously as a preliminary lectures, but let me refresh that knowledge very quickly. So we have already discussed that what is intrinsic silicon or intrinsic semiconductor. Intrinsic silicon is pure silicon. So if I have a material, a solid material, I model that solid material like that it is made of silicon atoms, and I have shown those atoms almost like a periodic array or arrangement of atoms. So I can represent like, because everything is made of atoms, so classically I can represent a solid like an arrangement of atoms which are present very close to each other. So this is the solid material and it is intrinsic silicon. We have already discussed it. It is made of pure silicon atoms. And we have already discussed that when a solid is formed and we show the arrangement of atoms, like a solid is made of atoms and the arrangement of atoms is similar to this one. So I told you that silicon atoms in the solid, they make covalent bonds with the four neighboring atoms. For example, here I have a silicon atom. So it makes a covalent bond with the atom above it. So it will share its electron with the neighboring atom above. And similarly, it will share one more electron with the atom on the right. Similarly, it will share electron with the atom below it, and same is the case for the atom on the left. And here is also the same case, that it will make covalent bonds with the neighboring atoms. And I told you that covalent bond is the bond where an atom shares its outermost or valence electron with only the neighboring atoms, not all the atoms. Unlike the metals where an atom shares its electron with all the atoms present in the material, and same is the case for every atom present in the material. In the semiconductor, covalent bond is present, and in the covalent bond an atom shares its valence electron with only the neighboring atom. So here the situation is perfect. A silicon has four valence electrons, and and all of those four electrons make covalent bonds with the four neighboring silicon atoms, and situation is perfect. All the electrons are bonded through covalent bonds, and the situation is just perfect. And in this situation, a silicon behaves like almost like an insulator, because all the electrons are engaged in covalent bonding. And once they are in where they are bonded, it's not easy to force them to flow through the material or move, because it's not easy to snatch them, because now they are bonded. If an electron is in the valence shell, then it's a bit easy to snatch it from its nucleus, but now it is shared with other atom through a covalent bond. So this situation is very stable and it's not easy. And also remember that this is the case with all the atoms. All the atoms, they share their electrons with their neighboring atoms. So same is the case with it, will share an electron above it, because I cannot show all the electrons, although at the edge the atoms will not be able to make a covalent bond when we will reach at the boundary of the material, but that is not to our concern. For all the materials within the solid, they will make covalent bonds with all the neighboring atoms, and all the four electrons are engaged, and it's not easy to conduct electricity through that material. Now here is the magic. We have already discussed that if I have a trivalent atom and I inject that atom into this pure or intrinsic silicon, if I have a trivalent material, for example boron, it has a trivalent material is a material in which it has only three valence electrons. And I inject this trivalent electron into the intrinsic silicon. On the other hand, if I have a pentavalent atom, a material, pentavalent is a material which has 5 electrons in its valence shell. And if I inject this atom into this material, what happens? And these two procedures, if I inject with a trivalent material or I inject a pentavalent material, I make two types of semiconductors. One is P type, another is N type. And then here we will see what happens. And for example, if I replace this silicon atom with a trivalent atom, and then what happens is very interesting, that it makes covalent bonds with the three neighboring atoms because it's a trivalent material. It has only 3 electrons in the valence shell, so it makes a covalent bond with the 3 neighboring atoms, 3 neighboring silicon atoms. But then it can't make a covalent bond with the 4th atom. It is left because it doesn't have any electron to make a bond with the next neighboring silicon atom. So there is a vacancy for the electron because it is asking whether I need an electron so that it can make a bond. So we call this space like deficiency of electron because there is no electron, but it is wanted. Electron is wanted at this place, but unfortunately it is not available. So we call it hole. So now it has become N-type semiconductor or extrinsic semiconductor because P-type semiconductor. Similarly, if I do a different process on the right side, for example, I replace a silicon atom from the middle and I replace it with a pentavalent atom from a material like phosphorus, now something else happens. It will make covalent bonds because it has 5 electrons in its valence shell. So it will make a covalent bond with the 4 neighboring silicon atoms, for example here and then this and with the lower atom and then on the left side. And now the problem is that one electron is left because this is not silicon atom, it is phosphorus atom or any material which has 5 electrons in the valence shell. So one electron is left, and if I replace many atoms with the pentavalent, it will get overall many electrons. So we gave it a name N-type semiconductor. So now if I replace many atoms, many silicon atoms with the pentavalent and on the left side with trivalent, I get P-type and N-type materials, and they will look something like that. When I will dope an intrinsic silicon with trivalent, I will get so many holes. So these black circles are showing that this material has so many holes. Similarly, on the left side, you can see these E circles, and with the E, they are showing that there are so many extra electrons which are not bonded and they are free, because if an electron is not bonded, it's almost free. Similarly, on the left side where we have a p-type material, it has so many holes, mean the vacancy for an electron. This material is looking for electrons. On the other hand, on the n-type, it has excess number of electrons. And also see that the charge carriers in the n-type are free electrons because it has a lot of electrons. So if a current flows in that material, it should be because of these free electrons. Similarly, for the p-type material, majority charge carriers are holes. You see, there are no free electrons available. So if a current is flowing in a p-type material, what could be the reason? These are actually holes, because when you connect a voltage source across this material, the electrons will run and rush to fill these holes, and as a result a current will constitute. You will see the current is flowing. That current is flowing because of filling these holes. So we give it a name that the majority charge carrier in p-type material are holes. Similarly for the n-type, because these are excess number of electrons and they are actually flowing through the material, so we say that the majority charge carrier in the n-type are electrons. It means the current, the reason the current is flowing in that material is because of electrons, and for the p-type the reason the current is flowing in that material, if any, is because of the holes, because it has excess number of holes. So now if I bring p and n-type materials together and they are in contact with each other at the molecular scale, what do you think will happen? Here is the magic, because don't take it very lightly. It is really interesting phenomenon. If I bring an p-type and n-type two materials, they bring them in contact with each other at the molecular scale, what do you think will happen? As I told you that the p-type material is in want of electrons because it has a lot of holes. Holes mean a vacancy for the electrons. So it is looking for electrons. On the right side of the n-type material, it has excess number of electrons. So what could happen? So a diffusion will occur. So don't take it like they will mix up each other very in a random matter. No, they will diffuse because we are we are joining them together at the molecular scale. So diffusion will occur. Diffusion means slowly they will mix up slowly. So what will happen? Of course, the electrons on the n-type will rush to fill the holes on the p-type side. Similarly, this electron will go slowly and fill up. It's not that slowly, but it is like they're diffusing. So they're slowly diffusing. Electrons are filling holes on the p-type because it is looking for electrons. Now what will happen on the n-type? Do you have any idea that what will happen on the, because now here electrons are missing. So some electrons have been gone to the p-type or p-type side. So this material will have overall positive charge. It will gain a positive charge because now electrons have been transferred to the n-type side. And similarly, the n-type side will gain a negative charge, right? Because it has acquired some electrons and charge of electron is negative. So it means it has gained some negative charge on its side. So now n-type has gained some positive charge and p-type has gained some negative charge, and now here is the magic. And that magic is when some of the when the electrons will start diffusing to the p-type, and then a charge will be accumulating on the left side, a negative charge. Similarly, the n-type will be acquiring positive charge. Then these charges will distribute themselves across the boundary like this. They will become in a series and not randomly oriented. They will become in a well-mannered series, and we know that when there is a positive charge and negative charge, there is an electric field between them, which starts from positive to negative. So the diffusion of electron from the n-type to the p-type will start slowing down. And do you know why? Because now charges are setting up across the boundary. Positive charges are setting up on the n-type and negative charges are setting up on the negative. Then an electric field will be formed between them. So as a result, the negative charges, the remaining negative charges on the n-type behind this behind this setup of charges will start slowing down. The diffusion of these charges will start slowing down because of this field, because now there are negative charges here, and these negative charges will not allow the leftover negative charges to come to the p-type. And same is the case for the positive, or the for the holes to be filled by these electrons, because electrons, they cannot now cross this barrier which has been set up between positive and negative, because if there are negative charges have been set up, so an electron cannot cross this barrier because this whole path has been blocked by negative charges. And now if the electrons, free electrons from this type, from n type, if they cannot cross this barrier, so we call this area which has been set up between positive and negative charges a depletion region, because it has been depleted of any charges, because we know no charge can exist between the positive and negative charges electric field, because now we have a series of positive charges on one side, and then we have a series of negative charges on the on the p-type, and electric field has been set up between them, and no charge can exist in between. If you ever know, it is a type of very tiny capacitor, if you remember from your previous knowledge. And no charge can exist, because if there was any charge, it would be either attracted by one side and and it will be repelled by the other side. So no charge can exist in the region between this setup which has been made at the junction of these two materials. That is why we call it a PN junction, which has been formed between p-type and n-type semiconductors. And this is called depletion region, because no charge can exist, and a time will come where this diffusion of electron will slowing down, and at last it will just stop, because an electric field has been set up between these two charges. Here I have a clearer picture of the situation. An electric field has been set up between the distribution of charges across the junction, and this electric field will get stronger and stronger as the diffusion is going. But at the same time, this electric field will slow down the diffusion, because now there are negative charges here. And these negative charges will not allow further electrons from the n-type to go to the p-type. Of course, you know, because of that fundamental repulsion from the same charges. So slowly the diffusion will decrease, and at one point it will just stop. So now the electrons are trapped in this region of n-type, because they cannot make through to the p-type because of this electric field set up in the middle. And if an electron wants to go to the p-type, he has to cross this barrier, and this barrier has a certain electric field and voltage. And if it is silicon, then for the silicon this barrier voltage is about 0.6 volts. So, and if an electron wants to go to the p-type, he must have a force greater than the force offered by this potential barrier. So, and such a setup is called PN junction, and this, it has been a miraculous discovery for the field of electronics, and you will see that what happens with this setup when we connect the terminals of a battery across this setup. Now let's see what will happen if I connect ends of a material like P and N type, and they have been combined at a molecular scale and a p-n junction has been formed. So now I want to connect one end of this setup with the other end of the battery, and I want to see what will happen. So don't forget, there has been a potential barrier, and if it's silicon, then the voltage is about zero point 0.6 volts, the electric field setup at the junction. And this is in case of silicon, and at the room temperature it's about zero point 0.6 volts. Now my question is, here is the positive terminal of the battery, here is the negative, and I connect positive terminal of the battery with the p-type side of this material and negative terminal of the battery with the n-type side of the material. So what do you think will happen? So see, the negative terminal of the battery is filled with negative charges, and these negative charges will push these free electrons in the n-type to move to the p-type side. However, they will face a resistance because of this barrier. You can see this 0.6 volts as negative terminal is here and positive terminal is here. You can think this potential barrier as a battery whose terminals are reversed. Negative terminal is here and positive terminal is here, and the voltage of this battery is 0.6, but terminals are opposite to the voltage applied by this battery. So of course this negative terminal will not allow this electron to pass through. But now it depends on the voltage of this battery. So the voltage of this battery is usually 1.5 volts. So now what you think will happen? This 1.5 volts is greater than 0.6 volt, which is the barrier, potential barrier of a silicon PN diode. We sometimes give it a name diode or a PN junction. So if it is 1.5 volts, it means the push from the electrons in the negative chamber of the battery is enough to force the electron in the n-type to pass through this barrier and go to the other side of the junction, which is p-type. And then here they can just fill the holes or do whatever they want to do. It means the current will start flowing. So suppose if I have a control over the battery, for example, I replace this battery with another battery whose voltage is 0.5 volts, you will never see the flow of current because 0.5 is less than 0.6 volts, the potential barrier for a silicon PN junction. And these electrons or the negative side of the battery with 0.5 volts will never give a strong push to the electrons in this region to cross this barrier and go to the other side of the junction, because when they cross the barrier you will see that current is flowing. Otherwise no, they are just in prison in this region because of this barrier which has been set up as a result of joining these two types. In this mode we call it that this PN junction is in forward bias mode. When you connect positive or the p-type side with the positive terminal of the battery and negative side with the negative n-type side of the PN junction, it is in forward bias mode, and in this case you will see the flow of current as long as voltage of the battery is greater than the voltage of the potential barrier, because silicon is the commonly used material for PN diodes, but there may be some other materials, for example germanium or any other material. So you have to check what is the potential voltage of the potential barrier, and if you want to see the current flow, find a battery whose potential is greater than this potential barrier and then connect p-type side of the diode with the positive side of the battery and n-type side of the diode with negative side of the battery, and you will see the current flow. If voltage of the battery is less than the voltage offered by the potential barrier, you will not see any flow of current because the push to the electrons in the n-type is not enough to cross the barrier, because there are negative charges on the other side and they will not allow them to cross this barrier. Now, what if I reverse the terminals of the battery? Now, positive side is here, negative is here, and I connect the positive terminal of the battery with the N-type side of the PN junction and negative to the P-type side of the junction. What do you think will happen? The positive, and here are the majority carriers in the N-type are electrons. In the P-type region, majority carriers are holes, mean the deficiency of electrons. So what do you think will happen? It's easy to imagine that no current will flow across this junction, because here we have a positive side, and it is even worse. It will, because we need to push these electrons to cross this barrier which has been set up when the P and N type side was joined. So we need a push to these electrons in the N-type side behind the barrier. But instead, it will suck these electrons out of this region. Just in a sense, if you think like that, that instead it will just suck the electrons out of this region, and same is the case here. You can see like the negative charges may just flow to fill the holes here, but actually there is no flow of current across the PN junction or the whole setup. Actually, there is no flow of current, because flow of current will constitute if something crosses this barrier which has been set up in the middle. If nothing is crossing this barrier, there is no flow of current across the device. And it is even worse, because now it is, instead of getting a push, the electrons in this region, they are being sent away, or they are being sent away from the barrier. So they will even in fact go away from the barrier, and we can see like this barrier is actually expanding now in the sense like that. And this setup is called reverse bias mode. And in this mode you will not see any flow of current. So there will be absolutely no flow of current, at least by the majority charge carriers. So here is a little twist. You may see a little current flowing through this device, and what you think might be the cause of this little current, because apparently there should be no flow of current, because this is the worst situation. Electrons are being pulled away from the barrier instead of pushing towards the barrier so that they can flow through the material and we can see the current. That little current will be from some defects or breakage of the covalent bonds. So there might be some free electrons available on the p-type side. When the p-n diodes are made, you can consider them like a manufacturing defect. It could be because of some temperature abuse or breakage of the covalent bonds. So there might be some free electrons available on the p-type side, although most of the stuff is present with the holes. There might be some or few electrons available in the p-type side due to some manufacturing defect. Just consider it like that. And if those electrons are available here, for example, now to this electron situation is same like the case of forward bias mode, because now here we have a negative side. So this electron will feel the push towards the right side, I mean towards the barrier. So when it will get the push, it will just go through the atoms, and if the push from the battery, of course push is greater than, because I told you the voltage of this battery is 1.5 volts. So although for the holes it is not the push towards the barrier, but for this free electron which is just existing in that p-type region because of some defect, it will feel a push towards the barrier. So somehow it will pass through the barrier if the push from this negative side of the battery is greater than the potential difference across this barrier. So it will just cross and go through the barrier. And because of these some leftover electrons on the p side, it is not only one electron, there might be some other electrons present, and because of these leftover electrons on the p side, you may see some little current flowing, but that current is not due to the majority charge carriers. Majority charge carriers are electrons on the n-type side. If an electron on the n-type side, which was already existing on the n-type side, and it crosses the barrier towards the left side, that current is because of the majority charge carrier, because if you see on the n-type, a lot of charges are free electrons on the n-type and holes on the p-type side. So this current is not because of majority charge carrier, it is because of minority charge carrier which are existing on the p-type side as free electrons, and this is called the reverse bias mode. And you can see, like, actually there is no flow of current because of majority charge carrier at least, and this current is too small and not of a significant value in most of the cases. We have studied the forward bias mode of a PN junction, that when we connect p-type side with the positive and n-type with the negative terminal of the battery, we will see a current flow as long as the voltage of the applied the voltage of the battery is greater than the voltage offered by the potential barrier. So it's not convenient to represent this figure in circuit diagrams. So we have a special symbol to show. The p-type side is shown with an arrow, and then the n-type side is shown with a vertical bar in front of it. So this is how we show this whole image, and the atoms and the barrier, everything is included in this diagram. So this is the diagram for a PN junction diode. So if I want to make circuit diagrams, I will show this symbol. For example, if I want to show this whole setup, I will show it like this, and then here is the diagram. PN junction, just remember that arrow is representing the p-type or positive side, and the vertical bar is negative. And if I want to show the circuit, you will know that we show positive terminal of the battery as a longer vertical bar, negative with a shorter vertical bar, and then I will connect it. So this is the circuit diagram of a PN junction diode in forward bias mode, positive and negative. Similarly, we have studied that in reverse bias mode, we will not see any current flow because of the majority charge carriers. And in this way, we can see that there is no current flowing through the PN junction. And once again, the P is with an arrow, and then vertical bar is representing the n-type, or I can write them as positive and negative terminals. And if I want to represent this circuit, I will just make the diagram of the PN junction diode, and I know that this is positive or p-type, and here is the negative or n-type side of the diode. And then here now I will connect positive or p-type side of the diode with the negative terminal of the battery, and positive terminal of the battery should be connected with the n-type. So this is also another way to represent this whole setup in this simple circuit diagram. So just remember the diagram picture of the PN junction diode and the sides, and everything is good to go. And I want to remind you of one more important thing, that the arrow is showing the conventional current flow. It is not the real current flow. Like in all of my discussions, I have been using the convention of real current flow, mean the electrons they usually flow through the circuit. But in the conventional current flow, we always assume that current flows from positive terminal to the negative terminal, and there is nothing wrong with the conventions. But whatever convention you use, just always use the same scheme throughout the area of studies or whatever you are doing. Never change it or never switch between two conventions. So whatever you adopt, just choose one and you are all good to go. You will get the same answers. Everything should be the same whether you solve numerical questions, as long as you keep the only one convention throughout the analysis or studies. Everything is good to go. So here the arrow is actually showing the direction of conventional current flow. But in all of my discussions, I have been using the real current flow. So just imagine that whenever you are talking about, for example, here the reverse mode, so current will flow opposite to this arrow. So just keep in mind that wherever you see the arrow, and if you are following the real current flow, just think that this arrow will always show, just if you want to know the direction of current flow, you have to go opposite to this arrow. For example, in the forward bias mode and in this circuit diagram, I will say that the current flows from negative to the positive terminal, but actually the direction of the diode is showing the opposite. So just keep that in mind. And it's also hard when you are dealing with the problems or the concepts related to PN junction diode. If you have a figure like this, it's hard to imagine what is actually going on. So I will try my best to show this image along with this circuit diagram so that you can see what's going on inside. And then slowly you will get used to it so that you will always get or understand the concept. If you are given a figure like this and I say that this is in forward bias, and because there are these free electrons, and if the voltage, if the applied external voltage is greater than the potential barrier of this diode, which is of course not visible here, then the electrons in the n-type region will flow to the other side, or the p-type of the PN junction diode. But it's easy to imagine in the figure, so I will try to present these figures as well so that you slowly get used to it. But always remember that when you are given a figure like this, imagine a picture like this at the back of your mind and then deal with those concepts. And the last thing, that what is so magical about PN junction diodes, the magic is that they allow the current to flow only in one direction, only in forward bias mode, and they don't allow the flow of current. Just forget about the minority charge carrier currents or drift currents. We are not dealing with them right now. So the PN junction diode allows the current to flow only in one direction, and it doesn't allow the flow of current in if the terminals of the battery are reversed or in the other direction. And this is the magic. If you remember, in one of my preliminary lectures, I told you that if you have a simple bulb, which we use it in daily life, and you connect negative or positive terminals of the battery with them, you will see that the bulb lights up. And I showed you this with the help of animations. And I also showed you that if you reverse the terminals of the battery, if you connect now the negative terminal here and positive terminal of the battery with the other side of the bulb will still glow. It doesn't matter if you reverse the terminals of the battery, the simple light bulb will always light up. But PN junction diode is different. It allows the current to flow only in one direction, and this is very magical. We will later see the applications of this behavior, and this is the actual magic of PN junction diodes. And don't forget when I say that the light bulb lights up no matter whatever is the direction of the current, or no matter how the terminals of the battery are connected across the bulb. I mean that when the light bulb glows up, it means it allows the flow of current in any direction, whether the current is flowing in this direction, or if I reverse the terminals of the battery and current is flowing in other direction, the bulb always allows the current to flow through it, but a PN junction doesn't. Graph is a good way to understand the values and how do they change. So here I have a graph paper, and I will see that how the voltage and current values of a PN junction change, or what is the behavior, because so far I have discussed everything in the words, like in a general way, but now we want to see like how really the values change and then compare the forward bias mode and reverse bias mode, because that is a systematic way to check or see the behavior of a device. So let's do that. So I will first see the value behavior of a PN junction diode in the forward bias mode. So I am connecting positive end of the battery with the P type, and N type is connected to the negative terminal of the battery, and here I have a schematic circuit diagram so that you can compare both of them. So you already know that this is a forward bias mode, because these negative electrons or negative charges will push electrons in the N type to cross this barrier and then go to the P type, and hence I will see the current. But because there is a reverse voltage because of the potential barrier, and let's assume that this PN junction is silicon, so this reverse voltage, because this reverse voltage is like a battery connected in with reverse terminals, and this is for silicon is around 0.6 volts. So let's see, and let's draw the graph of the values, because I am interested in current and voltage, that if I change the voltage, how the current will change, because we are interested in these two quantities. So I will represent voltage across the horizontal axis. So let's see, here I will plot voltage in volts, the unit, and I will represent current I, and of course this current is very small, so I will represent these values as milliamperes. Now I will set up the axes so that I can draw the values. So because this is voltage, so I will just write down the values. For example, here I have 0.2 volts, then 0.4 volts, then 0.6 volts, then 0.8 volts, and then I have 1 volt. And of course the values in between are like, if it is 0.2, then the first one is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1, because the space is limited, so I am just skipping one scale, one vertical line, so that there is enough space you can see the values. For the vertical, I will write the values as, if I choose this one is 20 milliamp, so I will write 20, the first one, and then 40 amps, and then 60 milliamp, and so on. Or I can just write 80, and then 100 milliamperes. So now the graph is set up, and let's see how can I see the values of voltages and the values of current and how do they change. So initially, as you know, that I am assuming that this PN junction is made of silicon, and let's just assume that I have this, it is just a fixed battery, and the maximum voltage for this battery is very low, but just assume it is a variable power supply, and I can change the value up to any value I want. Because here is 1 volt, so I just assume that I can change the voltage slowly. There is a knob which I can just rotate to increase the voltage slowly. So the first I just put the value 0.2. So at first just see that the voltage from this battery is at zero point 0.2. If it is zero point 0.2, so here is 0.2, and how much current will I detect if just assume that I have connected an ammeter in series, and it will tell me the value in current in milliamperes. So what do you think will I get the value? Because we don't need actually to do this experiment, but because we can just use our theory, we have developed an understanding of the behavior of PN junction. So now the applied voltage is 0.2, and then how much current will I get? I will get no current. You see that applied voltage is 0.2, but the barrier potential is 0.6 in case of silicon. It's around 6. So I will not get any current. Remember that even in forward bias, I have to cross this limit 0.6 volts so that the electrons in the n-type region will be crushed into the junction, and then they will cross the junction, reach at the p-type, and hence the current will start flowing. But now the 0.2 volt potential across the p and n-type, it will not have enough force to push the electrons across this barrier, because barrier has already an opposite potential of 0.6 volts. So if I am at 0.2, I will have no current, so I can draw a point here at 0.2, because current is 0 here at the origin. Current is 0 and voltage is 0.2, so I have this 0.2 dot. Okay, now I change the value to 0.4. Just assume that I am changing the voltage slowly. I am increasing the voltage out of this battery. What will happen at 0.4? Of course, 0.4 is still less than 0.6, and I will see no current out of my ammeter. So at 0.4, here is the point. Voltage is 0.4, but no current. And now see that I have changed the current to 0.6. Now what do you think will happen? Of course, at 0.6, still I will not see any current. So current is still 0, because the voltage is almost equal, but it's equal, right? I need a voltage greater than 0.6 so that the electron will flow, not equal. So next I change the voltage to, now the applied voltage is, now tell me what will happen. Here the magic will start. These electrons will have enough push or enough energy to cross this potential barrier in the middle, which has been set up as reverse voltage 0.6, and now the applied voltage is 0.8. So now I will see that current has started increasing, maybe around 40. Now these are hypothetical values, but of course we will see the increase in current, right? So it is at, just assume that it is around 30 milliampere. And just remember, these are hypothetical values, but behavior is similar. So now next, just see that maybe the voltage is 0.9. So at 0.9, here is 0.9. So I will see significant increase in the current, maybe around 70 milliampere. So just remember that the unit is milliampere. And then I applied 1 volt, and then of course I will see a surge in the current, because now electrons have much more energy than this potential barrier, and current will start flowing in this direction. And here is the circuit diagram. And now if I connect these points through a straight line, here is the graph. So now let's try to understand the graph. What does it say? It is showing the same behavior which I have already told you in my discussions and in words, but now we are seeing this, that voltage is 0.2, 0.4, but there is no current, and then something happens, some magic happens at 0.6, and after 0.6, when I cross this voltage, I see that current has started flowing in the PN junction. And then it increases as I increase the voltage, current increases very sharply, and that is a good behavior. to C, and then it goes to 100 milliampere. These are just hypothetical values, but you see, and then because after I increase the threshold or a point 6, current increases very rapidly. That is the important parameter. It increases really sharp because these are hypothetical values. So in the forward bias mode, we see that this length along the horizontal axis, which is showing the voltage values, this length is showing the width of potential barrier, which is present at the center of the PN junction. Longer the width, it means longer is the width of the potential barrier for that PN junction. This width is of course for the silicon PN junction diode, but if there is another material, for example germanium, it should be smaller. The length of these points, total length along the voltage axis, they will be shorter. If so, for example the threshold value is 0.3 or 0.4, then of course we will see the rise in the current at this point and it will go this. So every PN junction will have its own voltage and current characteristics, which we can always draw by doing the experiments. So this was all about the forward bias, and we see that it allows the flow of current. Now let's see what happens when I connect PN junction diode in reverse bias mode. So I have reversed the sides of the batteries, and now this is the positive end of the battery, and I connect it to the n-type side of the PN junction, and this is negative side. I connect it to the p-type side, and just assume that I have an emitter in series so that it will tell me the values of the current, and I have a voltmeter which will tell me the values of the voltages. And as I told you, that just imagine that I have a variable power supply where I can change the voltage values. I will start from certain values and then I will keep on increasing, and then I will note down the current values. I will populate a table, voltage values, current values, and I can draw those values here on the graph so that I can see the behavior of current when the voltage changes. So just assume that I am changing the value. Initial value is 20 volts. I have applied 20 volts, and as you can see that this is actually the opposite to the forward bias, because now here is the positive side, and this positive side will actually bring the electrons away from the barrier. In fact, we need to push this electron into the barrier so that they can flow and we can get the current. But in this setup, it is not possible. We are doing actually the opposite to forward bias mode, because now we are just bringing these electrons away from the barrier, and it seems like this barrier is actually increasing in the width. And same is the case on the negative sign. These electrons will flow to fill the holes. So if you fill the holes, they will decrease, number of holes will decrease. So you can see like this, we are actually increasing the width of this potential barrier at the middle. So if I apply a 20 volts, so I have some idea like how the voltage and current values will change. So around 20, as I told you, that ideally we should not get any current, and whatever voltage I apply, whether 20 volts, 40 volts, 60, 80, 100, whatever, there should not be any current. But you remember I told you that as we will still see some current, and that current will be that there may be, or it is always the case that there are always some electrons here on the p-type side. You can call them as leftover electrons, or they can generate, these free electrons are actually generated on the p-type side. Ideally they should not be there on the p-type side, but sometimes there is a breakage of covalent bonds, or due to some manufacturing processes there are some free electrons, and the quantity of these electrons is very minute. So just remember that one. So if, for example, there is a free electron in the n-type and you have connected the n-type here, so to these electrons it is same like the forward biasing mode. They will feel a push from this negative electric field from the battery, and then they will go, and then if the applied voltage, for example, is 20 volts, of course it's much more greater than 0.6 volts potential barrier, or whatever is the value. So they will easily pass this barrier and then they will come here. After crossing and when they enter the n-type, we will see a little current. And as I told you, the quantity of these electrons is way less than the majority charge carrier, mean the holes. So we will see almost no current or very little current. So when I applied the voltage, I will be almost zero. So I can just see it's zero. And I will, at the end, I will also ask you to compare both the results, because remember, this is one graph, but the scales are different. The scales on the right side of horizontal axis and on the upward direction of vertical axis are different. Here I am presenting values in milliamperes and here these are volts. But see on the left side, although the unit is volt, but see the values. I am applying 20 volts. Remember when we were discussing the forward bias mode, when I cross the voltage of 0.6, that is the voltage for the internal potential barrier, I saw a surge in the current, forward bias current, and the current was increasing even with the little volt. You see, about 1 volt, I was getting almost 100 milliamperes current. So current was increasing very rapidly after crossing the potential difference of 0.6 volts. But here I am applying 20 volts and still the current value is negligible or it's too small. Even my ammeter cannot find the value of that current because it is too small. And also see that the downward direction of the current, the unit is different, is microampere. So don't think like this 20 and this 20 is same. This is 20 milliampere and here I have 20 microampere, and I will show you a comparison later that what does it mean, that microampere and milliampere. Then I change the value here. Just imagine that I have a knob which I can adjust the voltage, and I adjust the voltage to 40 volts. Still no current, you see. So ideally, actually there is no current. And that's why I told you during the lectures that this current is not very significant. Although it is significant in some applications, but in our case or in our discussions, because we are mostly concerned with the forward current, this is not significant. So when I applied 60 volt across the PN junction in reverse bias mode, I may see some current here. And let's see, I applied 80 volts. Then I will see some current values, maybe around here. And see, I set 90 volts. Maybe I will see a current value around here. And then at 100 volts, I might get a current value about 30. And then I can connect these values with a straight line, and here this is the graph of voltage versus current values. I apply a voltage across the PN junction and then I measure the current, corresponding current values. I make a table, I just draw the values, and here is the curve. So now let's compare both the graphs. That in the reverse bias mode, for example, you get this 20 ampere around somewhere 90 or more than 90, around 90 volts. You see, I am applying very high voltages across the PN junction. For the forward bias, the voltage was very little. Even this simple battery, double A size battery, its actual capacity is 1.5 volts, and it is enough to flow the current. But when I want to use the PN junction in reverse bias mode, I need to apply very high voltage. This battery is not capable, but just imagine that I have another power supply and I am applying the voltages. That I started with 20 volts, 40, 60, around 40, 50 and 60 I saw some current which was flowing. So you can imagine that this current is because of the minority charge carriers in the p-type region. There were some leftover electrons, and then this negative voltage pushed them to cross the barrier to the other side. And because the number of these charges is way less than the number of majority charge carriers, so that's why the current is way too low. And then 20 microampere current, I just want to emphasize on the units, because this 20 microampere is not equal to this 20, because this 20 is in milliamperes. And if I want to give you a rough idea, 20 milliampere is equal to 0.02 ampere if I change the unit from milli to ampere. But 20 microampere is equal to 0.00002 ampere. Now I have presented units in both the milliampere and micro in the ampere, so that you can compare. You see that when I get 20 microampere, around 90 or more than 90, because this is just a rough graph, we don't have to be very precise. So I get reverse bias current 20 microampere or 0.00002 ampere at the voltage around 90 or more than 90. At 90 volts, I get a current about 30 microampere. Sorry, it's not 30, it's 20. And you see 20 microampere is 0.00002 ampere. But on the other hand, I get 20 milliampere current in the forward bias around even slightly greater than 0.6, or yes, even slightly greater than 0.6 volts. When I apply 0.6 volts across the PN junction diode in the forward bias mode, I get 0.02 ampere current. And when I applied voltage around 90 or more than 90, I get current around 20 or 0.0002 ampere. You get this 0.02 ampere around nearly equal to 0.6 volts. And if you want to get a very small current point, this one, you need to apply very high voltage greater than 90 volts or around 90 volts. So just compare these two scales, that they are different. Here the values are bigger. Here these current values are too small because the unit is microampere. But for the upper direction, the current is in milliampere. So you see in the reverse bias, the current is way too small. And you have to apply very high voltage, because you know the reason, because number of minority charge carriers are very small. It's not like that. So I just want to clarify one point. When I was making the graph of voltage and current for forward and reverse bias operation of a PN junction, here are the voltages for reverse bias mode. So technically I should write negative 20, similarly negative 40, negative 60, negative 80 and negative 100. Because this is the convention when we calculate the potential difference across the component. For example, in this case, if for one voltage is 0.2 positive, then if I change the terminals of the battery, that voltage will become negative. But because we were already discussing the reverse bias mode, and I showed you the terminals of the battery accordingly, so that's why I didn't put the positive sign with these numbers. But technically we should put the negative sign with all of the numbers. They are showing that now terminals of the battery are opposite to the case when the terminals were attached. In this case, whatever were the terminals of the battery in the case of on the right hand side of the voltages, on the left when you put a negative sign, it shows that now terminals of the battery are opposite to what you used for the cases on the right hand side. Last but not the least, when we keep on increasing the voltage in reverse bias mode, of course a stage will come that the applied voltage is too strong that even these minority carriers will move too fast, and then they will break other electrons from their covalent bonds, and then we will see a surge in the current. and that stage will come. Of course, it's very natural to understand. I told you that even for insulators or some materials which are not conductor at some time, but if we apply a very high and strong electric field across the material, of course that force will force the electrons, even if they are bit tightly bound with their nuclei. That external force will force them to detach themselves from their nuclei, and then they will start flowing. So this is the same behavior. We call it Zener effect or avalanche effect, that when you increase the reverse bias voltage up to a very high value, then these minority carriers will break electrons, other electrons which were actually bonded through covalent bonds, but now those covalent bonds will break and a lot of electrons will move towards the n type, and you will see a large increase in the current. And this is the behavior of PN junction in forward bias mode and reverse bias mode. And now you know, and you can compare that how the forward bias mode and reverse bias mode, they are different. In the forward, you just need very small voltage to get very high current. But in the reverse bias, it's actually off. So if you are roughly speaking, I can say that it can allow current to flow only in one direction, and when you change the terminals of the battery, there is actually no current, because these current values are way too small, although they are also important in some specific applications, and we may discuss them in the next sections. But you can see the difference, that forward bias mode, the current you get in the surge in the current is way too long, and here you have to apply very high voltage to get very little current. And don't forget that the ability to let the current flow only in one direction and not in the other direction, it has very important applications, for example, in rectification, which we will discuss in the next sections. Here, let's observe the behavior of conductors, and then we will see the semiconductors with the help of this animation and energy diagram. I have a battery here. I have set the voltage 0, and the ends of this battery are connected with a metal, and you know that metals are very good conductors, and we have seen in the energy level diagrams or the band diagrams that the valence band, here the lower one is the valence band, upper one is the conduction band, energy is increasing. Like I told you, the convention we use, that energy is increasing in the upper direction. Here are the electrons. This is just a hypothetical metal, so it is just showing that electrons in the valence shell. In the valence shell, there are some energy levels. Within the one shell, there are some other subshells, and that these are the energies corresponding to the other subshells. So here we have a valence band, and then we have a conduction band. And in the metals, if you remember that I discussed that the valence band and conduction band, they are actually overlapping with each other. So it means if the electron is in the valence band, it is like it is also in the conduction band, in the sense that it is almost free from its nucleus. It is very loosely bound with the nucleus, so it is almost free. So now here is that material which is connected, and then this wire is going, it is showing like the energy level diagram of this material is here. So now when I apply a very small voltage, you will see that current will start flowing, and you will even see here the electron in the valence shell are, just consider them that they are already in the conduction band, in the sense that they are very loosely bound, so they will start flowing through the material, and you will see that current is flowing. So even if I apply a very little current, 0.1 volt, you see that current is flowing. So electrons are coming out of the negative terminal of the battery, and then they flow through the material, and then they end up at the positive terminal of the battery. So because the voltage is very slow, so that's why the push to the electron is very slow. It is like if I have a water tank and I see that the pressure of the water is small, so I will raise the height of the water tank. So if the water is stored in a water tank which is very high, I will see that now the flow of the water is increased, which I call it as pressure. So here it's the same. When I increase the voltage, now it's 0.2 volts, 0.3, 0.4, or I can just change the value to 2 volt. And you see that now the current flow has increased. The number of charges passing through the unit area is increased, and you see that here in the valence band, electrons have jumped up to the end of the valence band, and we have already discussed that valence band and conduction band are almost overlapping each other, so it means they are in the conduction band. And now you see that they are flowing through the material and current is flowing in the circuit. So this is the behavior of a metal, and you see that conduction and valence band are almost overlapping with each other, and currents and electrons are flowing in the material because now they have jumped up to the edge of the valence shell where they can just leave the atom and flow in the material. Now I will change this material with plastic. If you remember, plastic is an insulator, and then see the difference. Now I am clicking plastic. It will change this material down there. It will change with plastic, and see what happens. Oops, the current flow has stopped, but why? And I can see the energy level diagram. Now there is too much space between the valence band and conduction band. Conduction band is empty and valence band is completely filled. It means electrons are tightly bound with their nuclei, and it's hard to force them to move in the material. So I am still applying 2 volts, and I cannot increase the voltage more than 2 volts. And I don't see any current flowing through the material because this orange material is plastic now. And we see that all the energy levels are completely filled, and electrons are not loosely bound. Now they are tightly bound, and I see that there is too much space between the valence band and conduction band, and I need huge energy to give to these electrons so that they can jump to conduction band, and then I can get some current flow. But unfortunately I don't have enough voltage. I can only apply 2 volts, and with 2 volts I don't have enough energy to make this electron jump to the conduction band, and there is no current flow. Once again I am changing to the metal so that you can see the difference. You see the current, the electrons, they immediately went to the end of the valence shell where they can just start flowing through the material. And it's like the same, that valence, they are actually in the conduction band, because I told you that valence and conduction band, they overlap in metals, and now this is a metal. And when I when I make the voltage 0, you see that the electrons, they just move down to the valence band, and there are few energy levels, and this energy is of course very small. Even I apply very tiny voltage 0.1, they just jump to the next level, edge of the valence shell, and they start flowing the current. When I do 2, and if I increase slowly, now you see electrons, they just go to the end of the valence band, and now it's very easy to make them flow because they are almost free. So here I have a question for you, and my question is, here I have a p-type semiconductor, I have a battery, and my question is that what if I connect the positive terminal of the battery with one end of p-type semiconductor and negative end of the battery with other side of the p-type semiconductor or silicon? What you think will happen? You know that a p-type semiconductor or silicon is a material in which I dope intrinsic or pure silicon with a pentavalent atom like boron. They have 3 valence electrons, and then when they make covalent bonds with other neighboring atoms, a vacancy for an electron is left with other silicon atoms, because silicon has 4 electrons, pentavalent atom like boron has 3, so it makes 3 covalent bonds with 3 electrons of the neighboring silicon atom, but 1 vacancy is left because it cannot make bond with the 4th silicon atom. We have discussed it in detail. So my question is, if I connect a battery like this, positive terminal with one end, negative terminal with the other end, what do you think will happen? Will the current flow or it won't flow? So let me help you with an animation. Here is an animation. I have a battery and I have applied plus 4 volts. Here is the positive terminal of the battery. Here is the negative terminal of the battery. Here I have p-type silicon, n-type silicon. So my question is about p-type silicon. So I will put p-type silicon here and let's see what's happening. So yes, current is flowing, and if I see the energy level diagram, uh, when we usually talk, we say that the electron, they jump into the conduction band in case of semiconductors, and then they flow, and that's how the current is produced, or current flows through the semiconductor. But here what I can see is that the electrons are flowing and current is flowing through the p-type semiconductor, and I have applied a 4 volts voltage across the material, but electrons are flowing inside the valence band. Here is the conduction band, and they should go to the conduction band and then they should flow through the material, right? This is how we usually consider the current flows through the material. But when I put a p-type material across and I applied a voltage source across it, I see that current is flowing very well. But electrons are still in the valence band. Why? And let me change the direction of the voltage. Now I am changing the direction of voltage. Now it's -4. Let's see what happens. Okay, current has just reversed the direction as expected. But electrons are still in the valence band. Why? Let me explain it to you. When we apply the voltage, here we have the positive terminal of the battery with here a negative, and you know that p-type semiconductor like silicon, it has a lot of vacancies of electrons, which we call it holes. And I told you that the holes are the primary or the majority charge carriers in p-type semiconductors. And the way that we use the energy diagram, that in valence electrons, and then when they get enough energy so that they can leave their nuclei, and then they start flowing in the material under the effect of applied external electric field. But here there are no electrons, right? Because there should be an electron which will get, it is bound with the nucleus, and then when it gets enough energy either through the heat or applied voltage, it will detach itself from the nucleus and then it will flow through the material. And then we say that when it is detached from the material, whenever an electron in the material, it gets enough energy to detach itself from the nucleus, we say that it is now in the conduction band, and where it can just flow in the material following the path according to the applied external electric field which is provided by the battery. But when we have a p-type material, there are no free electrons, right? Now there are no free electrons which you can give the energy and then it will move to the conduction band and then it will start flowing. So that's how it happens. When we have a p-type semiconductor and we connect a battery, I told you that you can consider p-type terminal of the battery as a chamber which has a lot of electrons accumulated in the chamber. So now when you connect a battery with the p-type semiconductor, this electron will flow to fill the holes in the material. So it will go and fill this hole. Then next time it will move to this hole. And then because it is under the effect of electric field, right? So it has to go to the positive end of the battery. But this is how it will go. Then it will fill this hole. It is a random process. Then it will fill this hole, and then finally it will end up to the positive terminal of the battery. Similarly, another electron, of course, a lot of electron will move together, not one by one. And then another, it will fill this hole, this hole, this hole, this hole, this hole, and finally it will move out. So this is how the current is flowing. So you see the difference. There is no electron in the material which is attached with the nucleus, and then it gets enough energy to detach itself from the nucleus and then flows to the positive terminal of the battery. Instead, battery is providing electrons, and then electrons move to fill the holes, fill, and then finally they go back to the other terminal of the battery. So this current is different. There is no electron which jump to the conduction band actually. So if a current is because of the hole, that's why we say that majority charge carrier in p-type semiconductor are holes, because this current is because of the holes. But there are no electrons from the material which are taking part in the current flow. That's why we say that if we have such situation, then that current happens in the valence shell, because of course in the material there are no electron which can jump to the conduction band. Actually battery is providing those electrons, and those electrons are moving, are actually filling the holes, and then they fill the next hole and next hole, and in this way the flow of electrons happens. And that's why when you have a p-type material and you connect terminals of the battery, we say that current is, or the flow of electron is happening in the valence band. So there is no role of conduction band in p-type material. And of course when you change the direction of the battery, it doesn't matter, it will just happen in the opposite way. Current will come out of the other end of the battery, they will fill the holes, hey, one second, third, they will move to the other terminal of the battery. So changing the terminals of the battery won't change anything except the direction of the current, right? So this is how it happens. When I change the direction terminals of the battery, same thing will happen, but just in other way around. And that's why, so always remember, for p-type material, the current flows, and then current flows, and the electrons, they flow in the valence shell. So they don't jump into the conduction band. That is the difference. And that's why we say majority charge carriers in p-type are holes. So now I have n-type semiconductors, and you know that in n-type semiconductor we have pentavalent, we dope pure silicon with pentavalent atoms like phosphorus. Pentavalent atoms have 5 electrons in the valence shell, 4 electrons make covalent bonds with the 4 neighboring silicon atoms, because silicon has 4 valence electrons, but 1 electron is always left, and because one electron is unable to make a bond with any atom, because no atom is available to make a bond with this electron. So we have a picture similar to this one. We have a lot of pentavalent atoms like phosphorus or others. So my question is, here I have the battery. So I have the positive terminal, negative terminal. I connect one end of this n-type material with the battery, and negative terminal of the battery with other end of the material. Now what will happen? Will the current flow? If the current flows, what will be the situation of that current, or can you try to explain the flow of that current with the help of band diagram like conduction band and valence band? Or first let me know if the current will ever flow. So let me show you the animation. So now this time I will put n-type material in this place, and yes, current is flowing. I have applied 4 volts across this material, and I see that current is flowing. And now the interesting thing is, electrons are in the conduction band, and this is how the current is flowing through the material. Don't forget, for the p-type, the current was because of the movement of electrons in the valence shell. They were not jumping to the conduction band, but now they are jumping to the conduction band, and this is how the current is flowing through the material. So what does it mean that now electrons are in the conduction band and the current is flowing? So let me explain it to you. So now here I have n-type material, and I told you that in the n-type material we have free electrons in the material itself. So now how the current flows is different than the p-type material. In the p-type material, we did not have free electrons or loosely bound electrons so that they can flow and constitute the current. Instead, battery was providing some electrons to fill the holes. But now here the situation is different. We have already loosely bound electrons which were unable to make a bond with neighboring silicon atom, the covalent bond to make the atoms, because in the covalent bonding, electrons share electrons with neighboring atoms. So in this case, when we apply the voltage or electric field, this negative terminal will force or give the energy supposed to this outermost electron, which was unable to make a bond with any atom. So now this electron will flow in the material. It will move here and there under the effect of gravity. And remember that this electron is from the material itself. And then it will move here and there and there and there, and this is how it will flow through the material. Similarly, another electron will move and then it will flow through the current. So when I say that this electron was attached with the atom of the material, and then I applied the external voltage or electric field, and then this electron was somehow able to detach itself from the material. It was in the valence shell, and now when it leaves its atom, it means it has jumped to the conduction band. That's why it is moving in the material. Otherwise, only electrons in the conduction band can move through the material. Otherwise, if it is attached to the atom in the outermost shell, it is in the valence shell according to the energy diagram. So now the current is because the electrons in the material itself are contributing in the flow of current. That's why we say that now electrons have jumped into the conduction band, and this is the way current is constituted in n-type semiconductor. And we say that the majority charge carriers in the n-type material are electrons. So that's why when we see this diagram, now it is showing in the energy level diagram that electrons or current is flowing because the electrons have jumped to the conduction band, because some electron in the material itself detached itself from the nucleus. First it was in the valence shell, but then somehow it gained enough energy to leave its nucleus and go to the conduction. When it is free, we say it is now in the conduction band, and now current is flowing. And once again, changing the terminals of the battery won't have any effect. It is just the same process, but now current will flow in the other direction, and I hope you can deal with it easily. Now let's see the p-n junction and forward biasing and negative biasing along with the energy diagram. So here I have a p-type material and I have an n-type semiconductor, and I can put them here to join them to make a p-n junction, and then I will change the voltage to see what happens. So at first I will try the forward biasing. So you see the battery, here is the positive terminal of the battery, so I will put p-type here so that it is connected with the positive terminal of the battery. This is how we use p-n junction. And in the forward biasing, you already know that current always flows after we apply the voltage which is greater than the internal potential barrier voltage. So now I have p-n. Now I am taking the n-type and just see that some current will flow at the moment. You will see on the left side in the energy diagrams that some electrons will flow from one material to the other, and that is there when they are making the potential barrier between them. When they are making the potential barrier, you know that the charges will diffuse across each other. So that's the time when you will see little current. But when the barrier is formed, current will stop. So this is, you will see. Now I am leaving it on this, and just have a look on the energy diagram. You see some electrons are moving. This is just a hypothetical figure, and you see that the internal force arrow, it is increased. It means some electrons have mixed up, diffused across the two materials, because one electron is in deficiency of electron, other has excess number of electrons, so they will diffuse. But the pattern of diffusion is like that. When they diffuse, they ultimately build up an electric field across the boundary of the two materials where they are combined, and as a result the further diffusion will stop and an electric barrier will be formed. So we saw that the silicon has a potential barrier of around 0.6 volts. Now the p-n junction has been formed, and you can see that as we saw that the n-type material is here and the p-type material is there. And let's see what happens when I will apply a voltage across this p-n junction in the forward bias, because you see p-type material is connected with the positive, and now I am increasing the voltage. You see I have applied 0.1 volts, but there is no flow of current? Of course, because I have to apply a voltage which is greater than the potential barrier voltage, and in this animation it is showing the internal force. The arrow is longer than the battery force. So I have to increase. So now see, the battery force is increasing here, and internal force which has been built up because of the PN junction is there. So I have to apply a voltage to surpass the internal force here, or the potential difference produced by the potential barrier, 0.4, 0.5. Okay, now I can see something is happening, because now internal force is almost like 0 and battery force is greater. It means I have crossed the potential barrier somehow, and you see that electrons are flowing, and I have already told you that the current flow in one material happens in the conduction band, and for the other material in the valence band because of the holes, and you are familiar with that notation. And now if I increase the voltage, of course the current flow will increase. You see, with just a little increase in the voltage, I get a big increase in the current. So if I apply a 4 volts, you see that now the battery force is too much. Internal force is almost 0 now, because voltage is too high, and a small barrier potential is nothing in comparison to this high voltage 4 volts. And you saw that the first time I got little current was around 0.5 volts, so it's nothing. So it is showing like internal force is almost 0, battery force is too much, current is flowing. And now you should understand the energy diagram, because I have discussed the separate cases for p-type semiconductor, n-type semiconductor, and you saw that for the p-type majority carriers are different, and in one material it happens in the conduction band, for the other the current flow happens in the valence band. And this is how it's happening, because two are together in forward biasing mode, so they are reinforcing each other. I mean, the current is flowing, but they are maintaining their nature of current flow in those materials. So now if I apply a reverse voltage, for example, now it's 4 volts. So if I apply negative 4 volt, the battery will change its terminal. So this is the convention we use in the voltage. If the voltage across some component is plus 4 volts, and when I say now apply negative 4 volts, it means change the terminals of the battery. So now I am applying negative 4 volt, and see what happens. I see that some current is flowing, right? But and then it has stopped. Now you know the reason. In the reverse biasing, I told you that you will see some current, and that current is because of the minority charge carriers. If you have forgotten, just see my previous lecture where I have explained the function of a PN junction, and especially where I have drawn the graph of voltage and current values for both cases. So when I say that the negative terminal, negative 4 volts, you see the battery has changed the terminal. This is the convention we use. So now it is in reverse bias mode. We see no current, and initially we saw some current. That was because of the minority charge carriers. But once the minority charge carriers are finished, you will not see any current flowing through the PN junction in the reverse bias mode. Let's talk about drift current. Drift current is the current which is because of the electric field of the potential barrier here. You saw that in the forward bias or reverse bias, whatever is happening, that current in case of forward bias is because of the external battery, which when we connect the terminals of the PN junction diode, that current is the main reason of the flow of that current is because of the battery, right? The drift current is different. You haven't connected any battery with the PN junction, but still you will see some current there. What is the reason of that current? And even in the reverse bias, I told you that you will see some current, a little current, and we call it, that current is because of the minority charge carriers. That minority charge carriers, not because of the majority, but you can see some current. And still the reason of that current is because of the external source, the voltage, external voltage you have applied to the P and N type side of the PN junction diode. But the drift current is different. You haven't connected anything with the PN junction diode, and I told you that there might be some free electrons in the p-type region, although it's rare and they will be in very small quantity. Majority of the charges are holes, as you can see, so there might be some free electrons on the p side as well, and just consider them as some type of manufacturing defect. And it could be, and there might be some the breakage of some covalent bonds as well. So if an electron is somehow present on the p-type side, and now it is wandering in the material, and you see that it cannot go to the barrier because there are negative charges, and these negative charges will push it back, and then it goes to the negative charge, they will push it back because of the repulsion. But sometimes it happens, there is a probability that it can sneak through, somehow it can sneak through this barrier. And if somehow it crosses the series of these negative charges, it can sneak through and it goes to in the middle of this potential barrier. Now it's easy. It will get a repulsion as long as it is on the left side of this vertical series of the negative charges. But if somehow it crosses this barrier, it can sneak through and it reaches in the middle. Now it will get a push from the negative charges towards the n-type. And at the same time, it will get an attractive force because these are positive charges, this vertical line on the right side. So this electron will get a push towards the n-type side as well as a pull from the positive charges on the right side. So it will immediately go to the n-type side. You see, it has crossed from the p-type side and it crossed the potential barrier and it has made its way to the n-type. So now you will see a little current because it is not only the one electron, there might be some other electrons like this who will make their way through the barrier somehow like this. If they just sneak through this vertical series of negative charges, the rest is easy. You see, this current is because of this potential barrier or electric field itself. There is no external source which is pushing this electron towards the n-type. So there is a small probability that such free electrons on the p-type side, we call them minority charge carriers, they can make their way to the n-type in this way. So that is called drift current. Drift current is because of the electric field which has been set up by the potential barrier and there is no external source involved. If there is external source involved, that is another current. It is not drift current.